Hello, I am Professor Kalpesh Patel, Electrical Engineering Department from the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Our subject is Control System Theory of the B third year 5th sem, and the subject code is 3130905. Our second chapter name is Time Response Analysis. This is the flow of contents. First one is the standard state signals. So in previous lecture we completed the first topic, standard state signal. So in this lecture we will conduct a time response of the first order and second order system for the standard states inputs. Analysis of the first order systems. Order of system is defined by the highest power of the s in the denominator. If in denominator the power of s is 0, so it is type 0 system. If power of s in denominator is 1, so it is type 1 system, and further type 2 and type 3 systems. So before studying the analysis, we should first know what is the meaning of order of systems. So basically the order of system is the highest power of s in denominator of a closed loop transfer functions. Now the time response analysis. Time response analysis indicate the system output response of the systems with respect to time. So this is the output system of the systems with respect to time. So it gives the what is the magnitude of the output at a different time intervals. So by definition, the response of a system to applied excitations is called the time response, and it is the function of the time. It is denoted by the CT. So here one example is given. This is the speed of the motor and this is the different times. Speed of the motor in RPM and this is the time in seconds. So here two lines indicated. One is the dotted line and one is a continuous line. So dotted line indicate the command input and continuous line indicate the actual speed of the motor. So first we assume that the command is given to the increase the speed of the motor at time t equal to 0. So this is the time t equal to 0. At this point, command is given to the system to increase the motor speed from 1000 rpm to 1500 rpms. So the speed of the motor gradually pick up from 1000 rpm to move towards the 1500 rpm. If command is given at t equal to 0, but the instance motor speed does not achieve the final outputs, it takes some time to reach at its desired outputs. So this is the response of the speed with respect to time is known as the time response analysis. So this is the command given to the system to increase the speed at 1500 rpm, but the desired speed, actual speed of the motor reach at this time. So up to this time it is the TS. So it is known as a settling time, TS. So this is time between the command given and the system achieve the desired output. This in between time is known as the settling times, TS. So the time response analysis is divided into the two parts. Before the TS time period is known as the transient periods, and after the TS time the desired output is obtained or the system becomes stable, this is known as the steady state times. So generally the response of any system has two parts. One is a transient response and second one is a steady state response. Transient response is the time before the system gets steady state, and after the transient period date, further period is known as the steady state time. So the definition of the transient response: the variation of the output response during the time it takes to reach its final value is called as a transient response of the systems, while the time period required to reach to the final value is called transient period, and it is denoted by the Ts. Second one is steady state response. It is basically the final value achieved by the system output. So the steady state response starts when the transient response is completely die out. The part of a systems that remain after the transient have died out is called the steady state response, and it is denoted by the CSST. Now the steady state error. The difference between desired output and the actual output of the systems is called as a steady state error, and it is denoted by the ESS. Suppose our desired output is 1, but the actual response is this, and after steady state this is not equal to the desired output. So this is the difference between the actual and desired is known as the error, steady state error, which is denoted by the ESS, and it is generally the 2% deviations of the desired outputs. 2%, that means if the desired output is 1, so steady state error is 2%. That means either 1.02 or either or 0.98. So this is 2% of the 2% error of the desired outputs. Now the analysis of first order systems. First order system, that means the power of S in denominator is equal to 1. So here only the power of S is 1. So this system is known as the first order systems. So consider the first order system as shown in figure, which has the input Rs and the output Cs, and unity feedback is given. So here negative feedback is used. Feedback is given to the negative sign of the comparator, so it is known as the negative feedback. So we have the general equations of this system is Cs by Rs, output by input, equal to Gs, which is the 1 over Ts upon 1 plus Gs Hs. Here is negative sign, so here we put plus. So this is the general expression for these systems. So referring this figure 5.18, Gs is 1 over Ts, Hs is the negative feedback, unity feedback, so it is the 1. So by general equation, Cs by Rs is equal to Gs upon 1 plus Gs Hs. So Gs is 1 over Ts divided by 1 plus Gs, and Hs equal to 1. So if we solve this equation, we get the Cs by Rs equal to 1 over 1 plus Ts. So this is the first order equations of the control systems. Now the type of system is given by the poles at adds equal to 0 of the system transfer function. So this is the type 1 system, because the in denominator power of S is 1. So it is type 1 systems. If it is type 1 system, so it is steady state error for the step input is 0. So we consider the unit step response of the first order system, because the in steady state error for step input is 0. So we consider only unit step in response. Consider unit step is applied as an input to the first order systems. That means unit step input RT equal to UT. Taking the Laplace of this unit step inputs, it becomes Rs equal to 1 over S. From equation 2, Cs by Rs equal to 1 over 1 plus Ts. If we put the value of Rs equal to 1 over S, so we get Cs equal to 1 over 1 plus Ts into Rs, and Rs equal to 1 over S. So Cs equal to 1 over 1 plus Ts into 1 over S. so it become 1 over s 1 plus ts. Rearranging these equations, so it is cs equal to 1 over s into the 1 over t divided by, if we take common t, so it is the s plus 1 over. If we divided this equation in two parts, that means it is known as the partial fraction. So cs equal to a by s plus b upon s plus 1 over t. So we get the partial fraction of this equation cs equal to a by s plus b upon s plus 1 over t. Now we have to find the coefficients a and b. So to find the value of a equal to s into cs, forgot this, and to find the value of b, this term forgot it. So b equal to cs into this, so b equal to cs into s plus 1 over t, where cs equal to the this 1 over s 1 over t divided by s plus 1 over t. So if we put the value of cs, a equal to s into cs equal to 1 over s 1 over t divided by s plus 1 over t. So to find the value of a, the denominator s equal to s becomes 0 at the s equal to 0, and to find the value of b, denominator of b becomes 0 at s equal to minus 1 over t. So if we put the value of s equal to 0, we get the value of a, and if we put the value of s equal to minus 1 over t, we get the value of b. So here we put the s equal to 0 to get the value of a. So this is s 1 over s divided by s into 1 over t divided by s plus 1 over t. So this s will cancel out. In remaining term, if we put the value of s equal to 0, so it is the 1 over t divided by 1 over t. So it is the 1. So value of a equal to 1. And to find the value of b, equal to cs into s plus 1 over t. This is s plus 1 over t, and cs equal to 1 over s 1 over t divided by s plus 1 over t. And to find the value of b, we have to put the value of s equal to minus 1 over t, so the denominator of the b becomes 0. If we put the value of s equal to minus 1 over t, we get the b equal to minus 1. So if we put the value of a equal to 1 and b equal to minus 1 in this equations, we get the cs equal to 1 over s minus 1 over s plus 1 over t. So if we take the Laplace of these equations, Laplace of this equation equal to the Laplace of 1 over s equal to the, suppose the value of a is, if a by s, so it is only the a, and Laplace of s plus 1 over t equal to e raised to minus at. So we get finally ct equal to this is the 1 and this is the e raised to at. So 1 minus e raised to at, where a equal to the minus 1 over t. So we get the ct equal to 1 minus e raised to minus 1 by at. Now the response of the different value for t, we get the suppose we consider the time constants t, 2t, 3t, 4t, 5t and infinities, we get the value of ct equal to 0.632t, and if we put the value of t, this t equal to t, so this tt will be cancelled e raised to minus 1, and we solve this 1 minus e raised to minus 1, we get a 0.632. If we put the value of t equal to 2t, we get the ct equal to 0.86. If we put the t equal to 3t, we get the 0.95 of 0.95. If we put 4t, we get ct equal to 0.982. If we put 5t, we get the 0.993. At infinitive, it becomes the 1. So at infinitive, the ct equal to 1. So it is steady state at infinitive. So if we put if we draw the graph, the graph of CT at different time t. So we get this kind of graph. So value of CT is within the 5% of final value at t equal to 3t. So at t equal to 3t, it is the 2% of the 1. At t equal to 3t, this is the 0.95, that means it is the 5%. And at 4t, it is the 0.98, so it is 2%. So in previous lecture, in previous section, I explained at 2% when the system response reach, this is the after this time known as the steady state response. So at 40 the system becomes steady state. So the generally 32 or 40 may be taken as the steady state response, because at 32 to 40 the system reach at the 95% to 98% of the desired outputs. So 30 and 40 is considered as the steady state time constants of the systems. Now the analysis of second order systems. Before studying the analysis of second order systems, we will discuss some important parameters related to oscillatory behavior of the system. Second order, that means the power of S in denominator equal to 2. So first we will study some important parameter of the second order systems. First one is the damping factor and natural frequency of oscillations. So the average system has tendency to oppose the oscillatory behavior. This is called the damping. That means the damping of the system is opposed the oscillatory behavior of the systems. And this tendency control the closed loop poles of the systems, and closed loop poles decide the response of the systems. That means damping control the response of the systems. Now the damping ratio. The damping is measured by the factor called as a damping ratio, and it is denoted by the zeta. So when zeta is maximum, it produces the maximum opposition to the oscillatory behavior of the systems. Third one is the natural frequency of oscillations. When zeta is 0, that means there is no opposition in the oscillatory behavior of the system, and the system will oscillate naturally. So at zeta equal to 0, the system oscillate with maximum frequency, and this frequency is known as the natural frequency of oscillations, and it is denoted by the omega n. Now consider the closed loop transfer function of the second order system as shown in figure 5.21. In denominator, power of S is 2. If we multiply this S, it becomes S square and 2 s zeta omega n. So this is known as the second order systems. So here Hs is negative feedback. So Hs negative unity feedback. Hs equal to 1 and Gs equal to this omega n square upon divided by S plus 2 zeta omega n. So general equation of this system, Cs by Rs equal to Gs upon 1 plus Gs Hs. If we put the value of Gs equal to this, Hs equal to 1, we get Cs by Rs equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. This is the general equation for the second order system. So poles of a closed loop transfer functions. So pole is, if pole is defined as the value of Cs denominator equal to 0. So denominator equal to S square plus 2 zeta omega ns plus omega n square equal to 0. So if we get equal to 0, so roots of these equations, S equal to twice A plus or minus under root delta minus B plus or minus under root delta divided by 2A. Here A equal to 1, B equal to 2 zeta omega n, and delta equal to B square minus 4AC, and C equal to omega n square. So if we put this value, we get the roots S equal to this. So here we get two roots. One is a minus zeta omega n plus omega n under root zeta square minus 1, and second root is the minus zeta omega n minus omega n under root zeta square minus 1. So the poles are real and unique if the value of this under root zeta square minus 1 greater than 0. That means we get the zeta greater than 1. So they lies on real axis. So it is the real and unequal poles. If we consider the value of zeta square minus 1 equal to 0, so this whole term become 0 and only minus zeta omega n. So zeta equal to 1. So this is known as the critically damping, and the poles are repeated on the real axis. In this, roots are in real axis but is distinct. So all the roots have different value. But in this, the roots are on real axis but roots is the same value. So it is the repeated on real axis. Consider the third case. If we consider the zeta square minus 1 less than 0, so value of zeta less than 1. So poles are in second and third quadrants. Now the time response of second order systems subjected to unit impulse input for the zeta less than 1 and zeta greater than 1. If zeta less than 1, it is known as the underdamped, and if the zeta greater than 1, it is known as the overdamped. So the transfer function Cs by Rs omega n square divided by s square plus 2 zeta omega ns plus omega n square. To find the pole, we have to put denominator equal to 0. If we put the denominator equal to 0, we get the two roots s1 and s2, which is this. But here is minus 4 omega n square, so it is j, plus or minus j. So if we consider omega n under divided by 1 minus zeta square equal to omega d, so we get the s1 and s2 equal to minus zeta omega n plus or minus j omega d. So this is two roots of the second order systems. Now we will consider the different cases depending on the value of zeta. First case 1, consider the zeta less than 1. So this is the underdamped systems. When zeta less than 1, then as per the equation 4, omega d will be present, and according to the equation 5, the roots will be complex in nature. So if zeta less than 1, so omega d present, and according to these equations, the roots are complex. Your input is unit impulse, that means Rs equal to 1. So from equation 1, so this is the equation 1. If we put the value of Rs equal to 1, we get Cs equal to omega n square plus s square plus 2 zeta omega ns plus omega n square. So Cs equal to omega n square s square plus 2 zeta omega ns plus omega n square. Now equation C we can rearrange as, if we rearrange these equations, so we get omega n square divided by, if we take the common omega n square, then we if we rearrange this equation, we get this kind. So first we have to add minus zeta omega n square and take common omega n square, so we get 1 minus zeta square. So multiplying and dividing by omega d, we get, if we multiply by omega d and divide by omega d, we get this kind of equations. So this omega d will be cancelled out, and if this become omega n square 1 minus zeta square is equal to omega d. Omega d equal to omega n 1 minus zeta square, so it is the omega d square. So Cs equal to omega n square divided by omega d divided by s plus zeta omega n square plus omega d square. So to obtain the equation of Ct, we have to take the Laplace inverse of the Cs. So if we take the Laplace of Cs, we get the value of Ct. And this is the standard equation of the Laplace inverse. L inverse omega upon s plus a square plus omega s square. So the Laplace inverse of this equation is equal to e raised to minus at into sine omega t. So here this is the same manner in these equations. If we take the Laplace inverse of Cs equal to Ct, so it is L inverse omega n square by omega d into omega d by s plus zeta omega n square plus omega d square. So this is the constant term. So we take outside of the Laplace inverse. The remaining term is same as this. So in these equations, a equal to zeta omega n. So e raised to minus at equal to, so e raised to minus at, e raised to minus a equal to minus zeta omega n t, and sine omega t. Here omega is the omega d, but omega d equal to the omega n 1 minus under root zeta square, which is assumed in previous sections. So if we put the value of omega d equal to this, the Ct equal to omega n square divided by omega d. Omega d equal to omega n under 1 minus zeta square, and e raised to minus zeta omega n t into sine omega d t. So we get the Ct equal to this 1 omega n is cancelled out, so it remain only omega n divided by 1 minus zeta square e raised to minus zeta omega n t and sine omega t dt. So this is the time response of the second order systems. Under this condition, the system is called as under-damped systems. Now consider the second case, zeta equal to 1, and it is known as the critically damped systems. If we put the value of zeta equal to 1, we have Cs equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. If we put the value of zeta equal to 1, so it becomes this, Cs equal to omega n square divided by s square plus 2 omega ns plus omega n square. So this is the solution of this s plus omega n square. So it is s square plus 2 s omega n plus omega n square. So these are same. So now the standard Laplace of e raised to minus at into t, it is 1 over s plus a square. If we compare this equation with this, so here a equal to omega n. So Laplace inverse of this, here omega n square is constant and 1 over s plus a. So here a is omega n. So e raised to minus at into t. So here t into e raised to minus a minus omega n into t. So this is the inverse Laplace of the Cs. Ct equal to omega n square t e raised to minus omega n t. Under this condition, the system is called as the critically damped system. Now consider the case 3, zeta greater than 1, and it is known as the overdamped system. When zeta greater than 1, according to the equation 5, the roots are real and unequals. We have the equation Cs equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. So this equation can be rearranged as, if we add zeta square omega n square and minus zeta square omega n square. So these equations and these equations both are the same. If we further rearrange these equations, so we get this kind of equations: s plus zeta omega n plus omega n under root zeta square minus 1, and second bracket s plus zeta omega n minus omega n under root zeta square minus 1. If we solve this equation, we get this kind of equation. So these equations and these equations both are the same. So using partial fractions, it is Laplace inverse is obtained. In partial fractions, omega n square is constant, and this is one term. So a by this and plus b by this. S plus remaining term is known as the A. S plus A. A is zeta omega n plus omega n under root zeta square minus 1. Here S plus A is this. So the Laplace of 1 over S plus A is e raised to minus AT. But e raised to minus A equal to the zeta omega n and omega under root zeta square minus 1. If we take common omega n, so it is omega n. Remaining term is zeta plus zeta square minus 1. Zeta plus zeta square minus 1. Same for this. S plus A. A is here omega n minus. So it is zeta minus zeta square minus 1. And so we get the Laplace of this equation is this Ct equal to omega n divided by 2 times. Here zeta square minus 1 is 2 times 4. So it is 2 times zeta square minus 1. So if we plot the output response Ct for the different value of zeta, first we consider the zeta less than 1. So we get this kind of output response for Ct. And this is the underdamped instance. If we zeta equal to 1, so we get this kind of response. This is oscillatory, but this is not oscillatory. If we further increase the value of zeta from zeta equal to 1 to greater than 1, so it is the overdamped systems. So this is the underdamped, critically damped, and overdamped. Zeta less than 1, it is underdamped. Zeta equal to 1, critically damped, and zeta greater than 1, overdamped. Now the G2 questions. First, derive the expression of the response of the first order system for unit step inputs and unit impulse. Is it possible to get the expression of response for impulse input if the expression is available for unit step input? If yes, then mention why. This may be asked for 7 marks in your G2 examinations. And write standard characteristics equation of the second order systems. So the standard characteristic equation of the second order system is the omega n square divided by s square plus 2 zeta omega n plus omega n square. Maybe asked in 1 mark definitions. Third one is explain with example first order system. Maybe asked for 3 marks in your G2 examinations. Last one is write the transfer function of second order unity feedback systems for step response and explain briefly each parameter of the equation. This question may be asked in G2 examination for 4 marks. So in this lecture we completed the second topic, time response of the first order and second order system. So in next lecture we will conduct the application of initial value theorem and final value theorem. Thank you.